Okay, so here's a question for you. Can we teach a computer to play the ultimate game of connect the dots, even if the picture it's supposed to draw changes every single time? Well, the answer is yes, and how we got there reveals this really clever trick that taught AI how to solve a whole new class of problems. So let's just dive right into the puzzle itself. All right, picture this. I just throw a bunch of random dots onto a screen. Now, what's the best way to snap a rubber band around the outside of all of them, so it's as tight as possible? So that little rubber band puzzle, it might look pretty simple, right? But in the world of geometry, it actually has a fancy name. It's called the convex hull problem. And believe it or not, teaching an AI how to do this, well, it's way trickier than you think. So what's the deal? Why would a powerful AI get tripped up by something that looks like a kid's puzzle? The problem, it's probably not what you're thinking. See, for an AI, the tricky part isn't actually drawing the lines. That's easy. The real challenge is that the number of dots you need to connect, the number of points that make up the final shape, it's different every single time. One puzzle might need 3 points to solve it. The next one might need 7. The one after that could need 20. The AI has no idea beforehand. It has to figure it out completely on the fly. And to really get why this is such a headache, we've got to take a quick look back at how older AIs used to work and why they just got completely stuck on this kind of problem. Okay, think about an AI language translator, right? It works by looking at a sentence in one language and picking words from a huge but fixed dictionary to create the translation. It knows every single possible word it could ever output. But our little connect the dots puzzle is totally different. The list of possible answers, the dots themselves, it's brand new for every single puzzle. The AI can't rely on some pre-made dictionary. It has to pick its answer directly from the inputs it just saw. So here's the bottom line. The classic AI approach for this stuff, what are called sequence-to-sequence models, they were fantastic for things like translation, but they had this one massive weakness. They needed that fixed dictionary of possible outputs. They just weren't designed for problems where the correct answer is a handful of items you have to pick from a constantly changing list of inputs. But then, researchers had one of those light bulb moments, an idea that started to change everything. It was all about teaching an AI a new trick, how to focus. And that breakthrough came from an incredible concept called the attention mechanism. You know how when you read a sentence, you don't give every single word the same amount of brainpower, right? Your mind naturally focuses on the important words to get the meaning. Well, the attention mechanism basically gave AI that same superpower. Instead of trying to process everything all at once, it could learn to pay more attention to the most important parts of the input. It could focus on what's relevant right now. And that was a huge step forward. Okay, so this whole idea of attention was cool, but it led to something even cooler. A truly brilliant trick that finally cracked this whole puzzle wide open. And here it is. This is the big idea. On the left, you've got the old way of using attention. The AI would look at all the dots, kind of mush all that information together into this general context, and then try to create an answer from scratch. But the new idea, the pointer network you see on the right, is so much smarter. Instead of trying to create something new, it just uses its attention mechanism like a laser pointer to literally point at one of the original dots and say that one, that's the next part of the answer. So how does this whole laser pointer thing actually work? It's actually super elegant. Step 1, the AI looks at all the dots on the screen. Step 2, it calculates an attention score for every single one of them. Basically, how important is this dot right now? Step 3, the dot with the highest score is where the laser pointer lands. And finally, step 4, boom, the AI selects that exact dot as the next point in the solution. It just keeps doing that, pointing from one input dot to the next until the whole shape is drawn. Okay, so it sounds like a really cool idea, right? Super elegant. But the real question is, did it actually work? I mean, did this pointer trick hold up in the real world? Well, the researchers put it to the test, and the results were pretty stunning. Just look at these numbers. They were dramatic. A standard AI model, an LSTM, got the perfect answer right less than 2% of the time. Basically, it was guessing. Now, adding that basic attention we talked about, that helped a lot. It jumped all the way up to almost 39%. But the pointer network? A whopping 73% accuracy. It nailed the exact right answer almost 3/4 of the time. That is a massive leap. And get this, when they just looked at how much of the correct area the AI's shape covered, even if it missed a point here or there, the pointer network solutions were 99.9% perfect. I mean, it was getting so incredibly close to the perfect shape almost every single time. But honestly, as amazing as that accuracy was, it wasn't even the most magical part. The truly mind-blowing result was something called generalization. This is the part that really changed the game. I'm going to read a quote directly from the paper because it's that important. They said, the learned models generalize beyond the maximum lengths they were trained on. So what does that mean? It means this is the key takeaway. They trained the AI on puzzles that had, say, up to 50 dots. Then they threw it a curveball, a brand new puzzle with 500 dots, 10 times bigger than anything it had ever seen before. And it could still solve it. This is huge. It means the AI hadn't just memorized a bunch of answers. It had actually learned the strategy for solving the puzzle. And this wasn't just for some abstract dot puzzle. They tried it on the legendary traveling salesman problem, where you have to find the absolute shortest route to visit a bunch of cities. So on the left, that's the perfect mathematically optimal solution. And on the right, that's what the pointer network came up with. I mean, look at that. They're nearly identical. It learned how to find an almost perfect answer just by looking at examples. So you can see, this breakthrough was about so much more than just solving a few geometric puzzles. It basically unlocked a whole new world of problems that AI could now tackle. So let's recap. What was the real contribution here? Well, first, pointer networks finally cracked that annoying variable dictionary problem. It taught an AI how to pick answers from a list that changes every single time. Second, it proved you can teach an AI complex problem solving just by showing it examples. No rigid rules needed. And maybe most important of all, it showed that an AI could learn a strategy so well that it could solve problems way, way bigger and harder than anything it was trained on. This discovery was basically the key that unlocked a whole new category of complex, real-world problems. We're talking about things like optimizing flight paths for an entire airline, planning the most efficient delivery routes for thousands of packages, or even helping design the layout of computer chips. All these incredibly complex logistical puzzles were suddenly on the table for this new kind of AI. And all of this leaves us with a really fascinating thought, doesn't it? If we can teach an AI to learn the abstract strategy for solving a puzzle this complex, just by showing it a bunch of examples, what other challenges, the ones that seem impossible to us today, could it learn to solve next?